Welcome to lecture 7.4. So we have example 1, solve the equation. So we're looking at when tangent of x equals negative root 3. Okay, so when is tangent of x equal to negative 3 in general? Well, we know tangent is negative. So tangent is negative in which of these quadrants? Quadrant 2 and quadrant 4. That is where tangent is negative. Okay, and then tangent is going to be root 3 over 2 at 2 pi over 3. So right about here, 2 pi over 3. And then in quadrant 4, tangent is negative at 5 pi over 3. So this is from our basic unit circle. Now, these are just some of the values for when tangent will equal negative root 3. So we know at 2 pi over 3, and then also at 5 pi over 3. But this is not actually our answer, and you might say, why? Well, if you recall, on the unit circle, what we're looking at is an angle, and then we can go around that circle how many times? We can go around that circle many, many, many times. So there are many times that our angle would end up with an answer that'll give me the coordinate, or the answer of tangent of x negative root 3. So we'd have multiples and multiples of some value here, and the value here. Which, this is normally 2 pi over 3, and we're just looking at the usual unit circle, and 5 pi over 3. But once again, we can look at multiples of these as we continue to go around and around the circle. So how do we take into account all of the possible solutions for this equation? Well, if I was to add pi to 2 pi over 3, that would give me the 5 pi over 3, right? And then if I added another pi to 5 pi over 3, I would get the new answer over here, which wouldn't be 2 pi over 3. It would end up being 8 pi over 3. Then I could add another pi and end up with some new value over here, and so on and so forth. So basically, if I added or subtracted some multiple of pi, where n is the multiple, I'll get the solutions for my equation. And there we go, that is the answer for our equation. So we have our value, 2 pi over 3, plus or minus any multiple of pi, and we'd slowly work our way to all the possible equations. Now you have to be careful, not all of the answers for the trig functions will just be by pi, so keep that in mind. Let's look at example 2, solve the equation. So 2 sine of x equals root 2. We want to solve for x, so let's go ahead and divide both sides by 2. And we have sine of x equals root 2 over 2. And we're not given any boundaries for this, so we know that there are multiple, many, many, many different answers for this. So where would they be on the generic unit circle? Well, sine is root 2 over 2 at pi over 4. And where else? And 3 pi over 4. That is where sine is generically root 2 over 2. Okay, but the problem here is we can't do what we did for tangent. We can't just create the 2 pi over 3 and then add pi to it all the time. Why not? Because if I added pi to this value, I would end up with some value down here, which would still be considered a possible solution, but I would skip this value no matter how many times I added pi, right? So that doesn't work. So how could I figure out how to include my 3 pi over 4 in the answers? Well, actually, we're going to end up having two different possible types of answers. We'll have x can equal the pi over 4 plus, and this is where we're going to do 2 pi k. The reason we're not going to just do pi is if we did boop here to pi, which I think I accidentally said was an answer, this would be negative root 2 over 2, which is not what we're looking for. So we can't just do one circle of pi, or sorry, one movement of pi. We have to go all the way back around to pi over 4 to get that positive root over 2, which is why we're going to add or subtract by 2n pi's, multiples of 2 pi. Okay? Or sometimes you'll see it written as 2k pi. Alright, so that takes care of that version of x, but once again, we still have to take care of the fact that we still get root 2 over 2 at the 3 pi over 4. So how would I figure out the multiples for that? Well, if I just go ahead and add a multiple of 2 pi, I'll come back to this value and find that new version. or multiple of 3 pi over 4, that still gives the answer root 2 over 2. Alright, so that's when we would have x equals 3 pi over 4 plus or minus, and we are doing 2 pi, once again different from tangent, we're doing 2 pi, and multiples of that. So I'll go ahead and rewrite it a little differently this time. K times 2 pi. Both of those versions of writing that works. Once again, we're just looking at all the options that would give us root 2 over 2. Now example 3. Find all the solutions for theta in the interval 0 to 2 pi. Okay, so here we go. Now we're given an interval. So before, notice for these ones earlier, we didn't have an interval, so we had to give all of the possible solutions, which is why we had to do this sort of arbitrary multiples of pi or 2 pi. But now we have an interval, so we may not have to do that. Let's take a look. So since we don't have to worry about getting multiples of our answer, we can just go ahead and solve this like we have before, and do sine inverse or arcsine of both sides. And then we'll have theta equals sine inverse of 0.2. So let's look at this on the calculator. So if you go ahead and graphing this on your calculator, the values I chose for my y equals were sine inverse and 0.2, and then the other y value I chose was sine of x. Once again, this is for the calculator. Then after that, for my window button, I did my x min, the minimum values for x, I did negative pi. X max, I did pi. Then for the x scaling, so how we scale the numbers, I did by ones. Y min, I did 0. Y max, I did pi. And then I scaled my y's by 1. And this I did by some guess and check, because in the beginning I had did both by pi, and that made it a little too big, so I had to change the y min to just 0. Okay, so when we go ahead and graph that, we'll get this, which is going to be the sine inverse of 0.2, and then I have my sine value, which will end up looking something like that. That these 2 points. So I want to figure out what those two are, because that is within our 2 pi, 0 to 2 pi values. Okay, so what would those be? With our calculator, we find out that theta is approximately equal to, let me change that color. Theta is approximately equal to, at the 1 point, 0.2014, and then theta is going to be approximately 0.29402. Oh, sorry, not that. I put my decimal in the wrong place. Approximately equal to 29.402, and those were the 2 points. Once again, we used our calculator for this because we didn't know those values on the actual unit table. Let's take a look at example 4. Solve the equation. So we have tangent of x equals 0.29, which we don't actually have a boundary for it. Okay, so we don't have some sort of interval like 0 to pi or whatnot, so we can't do it exactly like we did above, where we got exact answers. We're going to have to do it like one of these above here, where we ended up adding some multiple of pi, or 2 pi. In this case, since we're working with tangent of x, it's going to be multiples of pi. Let me go ahead and erase this because we don't actually have an interval. So solving for x, we'll just go ahead and take the tangent inverse of both sides. So why are we doing tangent inverse instead of like what we did previously, which was when we found the exact values? The reason is I don't actually know what the exact values are because I can't find them on the unit circle. So if I could find them on the unit circle, then means you can also find them on the unit circle. So if you cannot find them on the unit circle, that's when you'd use the tangent inverse, but if you can, you should be using the exact value. Okay, so we have x equals tangent inverse of 0.29. And then once again, since we aren't given a specific interval, we just need to go ahead and do multiples of pi for tangent. So just go ahead and say adding or subtracting some value times pi, and those would be the answers, whatever they might be. Multiples of pi. Alright, example 5, solve the equation. Okay, what is going on here? So we have, let's see, this one term being added to this other term and equal to 0. Two of them, okay, so we've got cosine and cosine there. and then just one sine. So let's see, I want to try and simplify this as much as possible. So let's see if I can put any of my algebraic skills to use. Well, I notice both of them have a multiple of 4. So I'm going to go ahead and divide both sides of this equation by 4. That means I'm left with 2 sine of theta cosine theta plus cosine theta equals 0. Okay, that simplified it. Next, I noticed earlier they both had cosine, which means I can factor cosine out. So cosine of theta, and then the remaining values is just the 2 sine theta and the imaginary 1. Once again, just using some algebra here. Okay, so now I have this fully factored, I can use the zero factor property, which means I set each term to 0 and solve. Now these look familiar. Okay, so solving cosine of theta equals 0. Well, when does cosine of theta equal 0? That would be at, let's go ahead and just draw a nice little unit circle on the side here to figure that out. So cosine is 0 here at pi over 2 and here at 3 pi over 2. We're not given a specific interval, so we have to do those multiples again. So we know that theta is going to equal, well, let's see, we know it's 0 at pi over 2. Now, if I added a multiple of pi, I could hit that other time when it's 0, and then I could continue adding pi and slowly hit all of the times that it's equals 0. So instead of doing 2 pi, I'm just going to go ahead and add pi. So we'll do pi over 2 plus 2, just plus n pi, some multiples of pi. Okay, so we figured that one out, solved that out. Now we have to continue solving for sine. So let's go ahead and subtract that 1 from both sides. Then we have 2 sine theta equals -1. Dividing both sides by 2. We'll end up with sine theta equals -½ Okay, so let's do another unit circle. When is sine equal to a -½ Well, sine is equal to a -½ at, let's see. So drawing in our unit circle, sine is a -½ here at 7 pi over 6. And also over here at 11 pi over 6. Now, I can't do a nice perfect addition item to end up here. I don't really know what that is, and normally we add by pi or 2 pi's. So I'm actually going to have to do 2 separate answers here. I can do 7 pi over 6, and then I'll get right back to it with multiples of 2 pi, so fully returning. So that'll be one option. Theta equals 7 pi over 6 plus multiples of 2 pi. And then, sadly, we're going to have to do the same thing, not really sadly, but a little more work, for 11 pi over 6, because I can't perfectly add to it to get to that other value, so I can't sort of double duty them. Which means I have to go on and add multiples of 2 pi to end up back at the pi over 6 value. So theta is going to also equal 11 pi over 6 plus n 2 pi, or k2 pi, depending on the book. Okay. And those are the 3 possible answers we have, and we had multiples because, once again, we were not given an interval to specifically find a value in. So let's take a look at the last example for 7.4. Solve the equation for sine squared theta equals 3. Alright, so let's go ahead and, how do we get sine squared by itself? That's the first thing we want to do. We'll go ahead and divide both sides by 4. Then we'll end up with the sine squared theta equals 3 over 4. Now notice, it's a little sneaky this time. We've got that squared going on there. So we'll have to take the square root of both sides, including the plus or minus. And then we'll have sine of theta equals plus or minus the square root of 3 over 2. 3 over 4. Which simplifies into sine theta equals plus or minus the square root of 3 over 2. So now we have to think, when is sine of theta positive root 3 over 2 or negative root 3 over 2? Let's take a look at a unit circle here. So, let's see. I'm going to rewrite this out, actually. So we have I'm going to do this in blue. The positive root 3 over 2 will be blue. So sine is positive root 3 over 2 at over here, which we'd usually call pi over 3, and over here at 2 pi over 3. That's when sine is positive root 3 over 2. Then sine is negative root 3 over 2 Okay, so sine is negative at these values down here. So it's negative root 3 over 2 at 4 pi over 3 and at 5 pi over 3. Okay, so now we have to figure out some multiples of these because they're not given a specific interval again. So how can we write the multiples? Well, if I start at pi over 3 and I add 1 pi to it, I'll get exactly, or directly to, 4 pi over 3. So I could go ahead and take away one of my answers by just adding pi's to these two, and then I'll slowly switch back and forth between these two, finding their multiples. So let's go ahead and do that for one of them. So we'll get that theta is equal to pi over 3 plus some multiple times pi, and then go ahead and we'll do the 2 pi over 3, and the same thing can happen. We can just add pi to end up at 5 pi over 3, and then another pi to end up right back there, and then slowly on with the multiples of each other. So we get that theta equals 2 pi over 3 plus some multiple of pi. Alright, and that is it for section 7.4. Please email me if you have any questions.